Welcome everybody. Myself Mukesh Oja from Qualcomm. I basically work as a kernel engineer there. So this topic is about. Uh, so this is a topic where this is secure remote proc. So Qualcomm has its own way of making a remote processor basically run in a secure validation because they authenticate the firmware and run it before that. So the image need to be authenticated before running it. So and it has been running basically many devices run with that. And so this is basically a problem statement where what happens to those devices when this Linux run at EL2. And basically so I'll go ahead with the agenda. So basically I'll go with the first the Qualcomm generic ARM64 software stack, and then we'll go how this driver call flow look like. Then how exactly it has been done when Linux run at EL1, and then what are the solution we have? We have found that, and then there is a use case when what happens when a remote processor basically has a dedicated assigned peripheral. Could be a DMA device which only dedicated for a remote processor. And then what is the challenges we are facing? That is why it is not a solution kind of thing, or that is the challenge we are facing, where how it's a Linux problem. We'll discuss what is the problem. So these are the some of the terminology which has been used in the presentation. So TZ stand for basically trust zone. We are calling trust zone basically any software which is run in a secure environment. We call it a generic term for the trust zone. TZ and remote proc anyway everybody knows. Then QE and QC is a Qualcomm terms, which is basically a Qualcomm hypervisor execution environment, and the same for the secure execution environment. SMMU anyways everyone. The PAS is a Qualcomm term. So there is a service which runs in a secure environment, that is a peripheral authentication service, basically which authenticate the firmware binaries. And there is HLOS, this is OS, basically we call it high level OS. And there is a SCM driver in Linux driver, which is for the code running at EL1, how it can be either trapped to a call to secure call either to the EL3 or EL2 directly. Then there is a pill and pass almost interchangeably it is used. Pill is a generic term, we call it peripheral image loader. So basically the driver which is been involved in the entire loading of the firmware and the authenticated, entirely generic term we use for the peripheral image loader. TFA anyway it is known. SSR is a subsystem restart. Subsystem here is a remote processor. So what happened when it crashes? It goes through a restart, and then SID is a stream ID. So this is how Qualcomm ARM64 software stack looks like, where apps are running at EL0, and the non-secure side and the secure side and apps. There is both side apps are there. One is secure apps, the other side TA trusted apps, and this side is a non-secure apps, app1, app2, and then there is a Linux kernel and the drivers. Then there is Gunia is a known thing now in open source. Still it is not merged in the Linux community, but Gunia hypervisor source code is in open code now. So, and which I was telling, right, QE, there is a BSP library basically run in there is one of the component, basically it's a QE Qualcomm, we tell it, and there is a pill drivers are there. This is a peripheral remote proc peripheral, this is a proprietary code. So the drivers which is there in this part of the code, and not everything handled at EL2. Then it has to pass to the secure world through this is called secure monitor, and then finally it will be land back for the call. The pass service is running there. So that is basically the authentication stuff which is part of QC. So the normal, how the call looks like, basically this is there are some drivers in there is a remote proc core, and that is the Qualcomm remote proc driver. Basically when a user space entity write it to the sysfs node which is there in the remote proc and remote proc number, and then the state. When it writes it, or it can be invoked even through a kernel clients, which will, it could be like ADSP or CDSP, remote processor, which we call as an example, or modem could be. So it could be auto boot itself, at the time of the probe of the driver itself, it can boot up. So, or either can be some kernel driver can invoke this remote proc booter. So what happens when the call will happen to the remote proc core? So the call will come here, and then finally it will land into Qualcomm driver. So what Qualcomm driver will do is it will there is a MTD loader, that is the format driver. Basically, it's not a driver; it's a helper module. Basically, the firmware binary will be calling the request firmware call will land here, and it, after that it will call TZ calls. Some of the secure calls it will make to the I said right, SCM driver is basically a secure channel manager, which will be calling for the secure calls that can either land to the EL2 or EL3. So these are the first two calls, pass init and mem setup, which is pass init and mem setup. Then it will land here. So same calls it will come. So when this will come here, then this is the secure EL1 code driver, Linux driver. Then it will trap to the Gunia hypervisor. Then the so what happened then, this call, because it has to be authenticated metadata, because first the call will be, the firmware binary will have a metadata, and then metadata will be, has to be authenticated as well. That too, the call will land to the, first it will be trapped by the hypervisor, then it will go to the EL3 monitor, and then finally it will go to the secure side EL1, where the pass service will be authenticating those images, and then it will come back, and then auth and reset will be called, and there also the authentication, the metadata first will be validated, then the real images will get validated. So same stuff, pass also get called for the real images, core images, basically firmware binaries. Then when the authentication, so as a part of auth and reset, so two things are called in a single call, where that is why this particular auth and reset call will be trapped in the hypervisor. Then the authentication will be done, and as a path, when the authentication is done, then there is a pill driver, as I showed, right? Those are drivers related to remote processor. Those land in those basically sits inside the pill itself, and that is where the reset sequence of the remote processor will start, and the firmware will boot. And after that, it will just Linux driver. It will come to the Linux driver, a remote proc driver, where it will wait for some time so that it gets the interrupt, so that firmware, remote processor has booted up. So, so this is how, if you have question, I can explain, because I feel like it's an interactive discussion. I could, because this is the generic code flow, and all things are spoken about here is upstream code, or Linux part basically. So the main thing, how Qualcomm does this thing differently than the Linux standard. Basically, remote processor needs resource table. Resource table are could be a device memories, which is needed by the remote processor, or could be a carve out, or could be some VirtIO stuffs which is there in the Linux kernel also. So what happened in for the Qualcomm firmwares, right? From the legacy firmware, the resource table, basically MMO resources which is needed by the remote processor, does not sit in the firmware binary itself. So this is how and because Qualcomm does this entire access control, wherever the MMIO region of either is a different remote processor or any access control stuffs, it either keep it at the TZ level, trust zone, or at the hypervisor level. So it wants to keep it at the one place. And so that is what statically maintains. And also there is the resources are, it could not be static, which is pre-known. It could be, there will be some resources which could be resolved at the runtime of the remote processor itself. So, and those resources are shared memory and all. Until it resolved, it also need to access some dynamic resources, that is shared memory, one of them. And then there is also, when EL2 runs, our Gunia hypervisor in control of the IMMU, and it does this entire translation control and configuration control of the uh, uh, of the table basically. So, and also for the remote processor, only single stage is implemented out of multi-stage, stage 1, stage 2, because it does not, it only stage 2, only single stage is needed, and that is what has been implemented. As I said in the starting, right, secure remote proc, basically the concept is image need to be authenticated before handing over to the firmware binary control to the remote processor. So that is the main concept behind making it secure. As I already spoke about this in the diagram, where these are pass in short form, pass init. Basically, it does this Qualcomm QCOM SCM pass init images. These are the calls which is sitting in the remote proc Qualcomm driver, where pass init is the basically metadata verification. Mem setup is basically it's optional if the image, firmware image, basically remote proc firmware image, are whether if it is not relocatable, it is not needed. It becomes optional. If it is relocatable, it need to be. There will be some subsequent action will be in the call, basically in the secure world. Then there is a auth and reset call where the entire memory region of the remote, which is the carve out where the firmware loaded, it will be locked, and there is a subsequent when the subsystem, when you call a start or shutdown. Shutdown call is the respective stop of the remote processor and or unlock the remote region. So what happens when the lock and unlock is basically if any memory region is accessed by the EL1, it will be XPU will happen. So is there any question if you, because next thing I'm going to explain when the same Linux, this becomes a problem when, because of the design, this entire thing will become a problem when Linux run at EL2. Basically, or example, you can take it as a KVM, basically. So, because earlier in that slide we have explained Gunya is in the control of the IMMU. Now, Linux has to handle this SMMU and translation, because it when Linux run at EL2, entire things is in control of the Linux at EL2. So how we are have implemented how to know that same driver need to work when Linux run at EL2, because as I said, right, some of the calls are trapped by the hypervisor, and if the Gunya entire thing, same diagram, if this EL2 thing will be removed, this Linux will shift here, and how the things which will be done here has to be done. Whatever things were done earlier, it need to be done at Linux level. Or there some stuff here as well. So now because Linux has the IMMU, Linux has the control of the IMMU. So a remote proc earlier in that current code where Linux ran EL2, remote proc does not have a IMMU property, and it's a optional thing to have. But now Linux need to be aware about the SID of the remote processor, and it need to be applied to the firmware stream. So now IMMU property need to be overlaid. So because same device can run under a Gunya hypervisor or when Linux had run at EL2. So same device tree need to be used. How will we differentiate whether Linux run at EL1 or EL2? Or same driver need to be used. So we have what we have done is now we have added an overlay node for the remote processor where IMMU property for the remote processor will be overlaid, and that's how remote proc code will come to know that if the IMMU property is there, then Linux run at EL2. That's how we are identifying at the moment, and that's how the entire thing driver will be aware that this is EL2 code, and that special handling will be done at wherever it is needed. Also, there is one more thing. Whenever some memory pass to the EL3, so that memory or buffer need to be, there is a secure SHM bridge concept where anything which is need to be accessed by the trust zone, it need to be, the memory need to be allocated from shared memory bridge. So this is the expectation of our TZE firmware. And now because Gunya was doing, whenever the metadata, the first pass init call land there, Gunya hypervisor used to create a SHM bridge, and then it passes the metadata to the TZ, which is EL3. Now Linux, because recently that And there is a TZ-mem driver which is same SHM bridge concept. It has been upstream. Now this will be helpful in doing the creation of SHM bridge when Linux run at EL2. So the SHM bridge creation, everything, this is upstream now. So that will help to create a SHM bridge concept while when Linux run at EL2. And now one more thing, this as I said, right, auth and reset is two calls. Authentication will go, and then authentication done, then Gunya will trigger a reset sequence for the remote processor. Now because Gunya is not there, the entire thing is driven from, or the reset call was driven from Gunya hypervisor, or basically to be specific, it is a QE firmware. So what happened in the, we have implemented this in auth and reset sequence to be, we have completely moved it to the EL3. Now because Linux at EL3, so in this code, this entire stuffs which is runs at this one, we shifted to basically here, somewhere this. So this is just the monitor. So what happens whenever the call will be made, it will be directly trapped to the EL3. And it will go to the pass, and same thing, entire pill driver, the pill driver here is moved to here. So, and that is why we are shifting it, because of this, make it EL2 independent. So any hypervisor could be, whether it Linux or Zen or anything, it could be. So we are making it independent with this. Now also, because as I said in the beginning, right, our firmware binary does not contain resource table, which is basically the resources of the remote processor. So what it does, and now we are getting, because this, as I said, right, earlier access control or entire MMI region of remoteproc MMI region were part of the Gunya hypervisor. There is access control driver is there in the Gunya, where entire thing is maintained. Now Gunya is not there, where to keep this information. So we are getting this, because as a pill sequence has moved to that secure EL1, now this is access control also need to be moved there. And we are getting a SMC call, which is parallel to another call, which will be giving this resource table information, which was Linux was not aware earlier, because it is entirely maintained in the EL2. Now Linux need to be known, because Linux run at EL2. Now it need to know that what are the resources. So we are getting from firmware, we have implementing a new SMC call, which Linux can call to get the resource table in Linux expected resource table format. So there is an resource table concept in our Linux, where the expectation is there should be a section in the firmware binary called resource table. And then that is a part of. So what initially, before going to this solution, we have been trying to the resource table, the entire memory region and the access read write or access information, flag information. We were trying to keep it we posted a patch where we have been asking for what should be the right way. So we in the RFC, which is posted here, we kept that in the device tree. So we are getting that entire resource table from the device tree, and we were applying those resources IMM mapping. Now Linux need to do this IMM mapping. Earlier it was not doing. Now it get the resources, and IMM map need to be applied for those resources. Now, but this was not liked by the community, and because it should not be kept in the. That was the obstruction we got from the community, and that is how that is what made us get a new SMC call from the firmware, which need to be implemented, and that will get the resource table in the resource table format. That is why this is the self things which I just explained there, Qualcomm. But yeah, it's not like Qualcomm will not be keeping the resource table in the firmware. It is not an immediate move, but in the future it will move. So we want to run some devices, older devices, to run Linux at EL2, could be KVM or something. So that is how, because the firmware, because resources, but by default the firmware which run at the older devices does not have resource table by default. Suddenly we cannot move it, because if I want to run those devices with the Linux at EL2, they will not be able to, and then their firmware need to be updated too, which we may not like to. So that is why we are getting this SMC call for those devices where resource table will not be a part of firmware. this thing I already told, right? This resource table need to be mapped before the author reset call is the same call, which I say after this Linux will hand over control to the remote to run the firmware. Now there is the use case which I spoke in the agenda where remote proc, remote processor can have its own dedicated peripheral, and it can, let's say example in the diagram, right? So it can have this is a DSP, which is a remote processor, and there is maybe multiple masters, which is peripherals we can say. And we are telling because they have their own SID, which is different from the SID. Here SIDM stream ID, different than that DSP. And so this could be multiple devices which is assigned to that DSP. And this is the firmware region. This is a memory carve out, which is a DDR memory. This DSP has a entire memory access for the firmware side, and and now the DMA memory. The DMA memory could be subset of the entire memory carve out for the remote proc. So basically, it has its own subset, and it has its own SID separate from that DSP. So this should not access the apart from the stuffs which is assigned to them. And so basically, firmware uses this DMA memory for the memory allocation to do the DMA thing, mem copy and all. So this could be multiple devices, and so this is the problem we have, and this is the one of the use case which we want to address. And for those use cases, when Linux run at EL2, that's a problem statement for us. And so the one things are I just explained mentioned in the slide, where could be DMA master 1 and 2, and it has its own SID, which will be different than this one. And same firmware allocates, and yeah, this memory could be changed. That is how it has been changed in the past for Qualcomm devices. This memory could be, because earlier this DMA memory was a part of firmware. Sorry. Now it has to be known to Linux, because there is a parallel. This use case need to be supported when Linux run at EL2. And how we would like to, we are thinking of a solution where how it could be addressed. So now, as I said, this should be this does not have access to that limited memory. Let's say, for example, DMA master 1 can access this DMA 1, DMA these memories, and the same DMA 2 can access this, but not the entire thing, because of the security reason and access protection. So it need to be access only those memory. So now the main agenda, this is the problem statement basically. This how to address those. We don't have a solution yet. We are looking for an idea how it could be done, and it's not a problem for Qualcomm. It's a Linux problem, basically. As I said, right, this firmware, now Linux need to know how this, what are those regions which firmware can use it for a DMA. So how it can be known, I mean, let the Linux know that these memory region exist. And because if we, let's say, as I said in the slides, right, that let's say if it is a part of the firmware, how it need to be identified is dedicated to that DMA, not the firmware. So that is the main problem. So as in the diagram, right, if the memory region known, let's say we assume that the resource table thing it's related to remote processor. But if you put the peripheral also, peripheral memory, which is a subset, also part of resource table, will not be able to know which one belongs to which one. So that's why if we keep it in the firmware resource table, that also does not seems to be a problem. So either something new need to be done. That's what one of the way where we were thinking of proposing this idea, but this does not also seems to where let's say this is the one node, how it looks like. Let's say it's a EDSP, audio DSP. And after this, there will be for remote proc can have its own IMM property. And this is the carve out from A to B example. There's a sub device. We were thinking of how if this DMA master could be a sub devices of this remote proc. And it could, we can, because I said that it could have its own SID, which we are this IMM property for the DMA 1, DMA 2, you can assume sub device 1, sub device 2. And there is a associated memory which is IMMU address. This is identical mapping, so it will be only accessing sub-device 1 and sub-devices 2. So, but the problem, right, because it's, if I keep it in a device tree, because I said this could change also. If let's say some memory region, the heap region memory need to be adjusted, that need to be changed also. So we cannot keep it, because we cannot change device tree frequently. So, and this is the one problem we have, and another problem is, as I said, right, this the translation stream need to be for that DMA need to be separate from the firmware. So it need to, because Linux DMA framework, Linux remoteproc framework has assumed it's only a single IMMU domain, and it does not addresses the problem of a multiple IMMU domain for a device. So it's a Linux problem. That's what I am saying, that it's a Linux, because it assume it there could be only one IMMU stream associated with the firmware, and there could not be any other than this. Other than that, remoteproc. Now, also, as I said, resource table entries, whatever mentioned in that. So whatever resource table which is part of firmware, that applies to that single IMU domain. So there is no support of multiple per group, like 2 DMA masters can access, and that should be access protected with the firmware. Those things does not exist in the Linux, and that's why we are looking for a solution where or advise how it could be done. So basically we have some idea about it, but it needs a change in device tree only, because now we have some resource table only, the way which we are thinking, where a resource table has some resource reserve bits, or also it also support the vendor specific customized vendor specific stuff as well, which could be explored. And that's how we can, because this IMMU addresses, even if we keep in our firmware, it need to be associated with some SID or something. And that information, if you don't keep in device tree, it has to be either told in the firmware binary itself, so that Linux could parse it, and specific information in that particular memory region to be that SID to be applied. So that could be the one way if we extend something, our Linux remoteproc firmware need to be made aware that about this, there are multiple IMU domain exist, and that particular memory region need to be applied to the particular SID, and for particular sub-devices, or not sub-devices, but basically DMA masters. So this is the problem statement we have, and we have not posted anything of this use case yet, but yeah, the last one where we posted about the RFC, where we are keeping the same resources in that form device tree. But this use case we have not discussed, and that is where we are stuck at for this, supporting the Linux at run at EL2, when Linux remoteproc at EL2. Yeah, this is the, I think we have, I think we don't have a solution. If you have, please suggest if we can do something in this area. But yeah, that's what we were thinking of, proposing something in the resource table only, because if we see, right, we have gotten way where SMC call could give resources in a Linux standard resource table format. So what is there in the form, with Linux parses the resource table section, which Qualcomm firmware does not have, but Qualcomm firmware, Qualcomm driver can get this SMC call to get the same standard as resource table thing. So only thing is, if resource table, the Linux standard, the resource table data structure, if need to be modified, and respective stream need to be applied to that DMA master or firmware, it could be just adding here stuff, because reserve bits, because if it is getting that in the resource table format, whatever the change we'll do for the Linux, it could be applied automatically here as well. So those devices where the older devices, where older firmware, where it does not have a resource table, it will still work for them. So yeah, that's it from my side. Basically, that was this panel discussion is about, I guess. So if you have any question, please reach out to me. Any question? Yeah. SA8775P.
So nothing else? Or?
No, yeah, this is the first one which because these things, right, the firmware will repeat for them as well. Whatever the changes, this is the first device which we are trying to solve, but whatever change we will do, right, it will be propagated there as well. So basically this is the, because Linux when run at EL2, audio, video, these stuffs does not work. So that is why we are struggling here. At least this statement, other things we have solved. So this is the one where these use cases where the DMA dedicated, remoteproc assigned peripherals. It could be anything. I'm just giving an example of a DMA. It could be any UART or something. It could be anything. So which has its own SID. Or
because I was wondering more about X1E.
X1V. Yeah, but yeah, we are trying the older device first. Then I said, right, it will be, this will also.
So will there be, do you need a new secure monitor firmware to be released, or how?
Yeah, that's what, the firmware change, because to be support, because entire stuff, Gunya thing will be not there. You have to update the entire, I'm saying, not the firmware of remoteproc, but the firmware of the secure thing, basically. Because
there are some, this EL2 bonds or whatever it's called. So that would work without the firmware changes, but I guess you still need.
Yeah, that idea you're saying, right? I recently some patches has been posted where that is how we got an idea that IMMU property could be overlaid, and there is separate DTB can be maintained for DTB overlay can be done for the EL2 awareness. That's how we got the idea of, you're saying, right? There is a patches there. I think Windows run at when.
Yeah, I think Windows Java has because of this VB as well.
Yes, same stuff. Yeah. So because the entire thing will not be there, right? So firmware need to be modified, and this movement of the code has to be done. Access control or a pill driver specific peripheral space will be moved there. So the firmware need to be modified, and Linux, what Ganya was doing, now Linux need to do. And that is how the Qualcomm specific support, which is, and it need to be aware. And because now we thinking that Linux itself does not support multiple, Linux remoteproc does not support multiple IMM domain. That is where we, and I think such use cases may not been mentioned. I have also posted a question in the community where if such use cases already somebody has faced, and if there is any suggestion already, but I did not get much idea, and that's the reason of discussing this here. So if such use cases exist, or a common problem to solve in that remoteproc framework where multiple IMU domain for an or single device can be explored or done. Any other question? Yeah, that's it from my side. If you don't have any question, we can. Okay, so basically we are anyway, first thing, so anyway we have to support this. So after that RFC we did not get, now we are getting this, some firmware calls. We will be posting patches for that, at least that resource table thing, get this from the firmware. But this problem statement still continues, and we will try to, maybe because now the problem here is basically now, even if we put a reserve bits in, there is a reserve bits in the resource table, which if we use, because each MMIO will have a device address, physical address, then the flag. It need to be aware this entire one memory related in access and that memory. It need to be associated with some SID, which need to, that is where I'm saying reserve bits, but or domain information. Some bits can be used, and that association we have to put it in device tree, so that some ABI can be made, so that this if they change, and so we may have a question for the device tree maintainers where if such thing can be, binding can be put in the device tree, and can this problem can be solved. Okay. Yeah, that's it. Thank you.